Welcome to this explainer. Okay, today we're going to completely rewire how you think about a mathematical concept that, let's be honest, usually strikes total unnecessary fear into the hearts of students and definitely causes some cold sweats during finals week. But actually, it's secretly the absolute superpower of every engineer on the planet. I'm talking, of course, about matrices. We're going to strip away all the complex jargon and just show you the brilliant, elegant logic underneath it all. Now, to understand why we even need them in the first place, just think about the sheer massive volume of data running our modern world. I mean, imagine trying to simply manage the grades of 200 students across 5 different courses. That's already a lot of data. Now, scale that way up. Imagine you're an aerospace engineer tasked with describing the exact position, velocity, and trajectory of literally thousands of satellites, simultaneously orbiting the Earth right at this very second. So, this brings us to a pretty fundamental question, right? How do engineers actually manage all this without totally losing their minds? If you tried to track all of those satellites using individual, isolated numbers, your tracking system and, frankly, your brain would completely crash. Individual numbers just aren't enough when you're dealing with modern, complex, overlapping systems. We really need a far better way to process reality. Okay, let's dive into this. Here's our roadmap for the explainer today. We'll start with Section 1, Beyond Single Numbers. Then we'll transition into Section 2, the matrix machine. After that, Section 3, the mathematical steering wheel, before zooming out to Section 4, Powering Modern Engineering, and finally wrapping up with Section 5, the language of relationships.
Section 1. Beyond Single Numbers. Organizing Information.
Imagine a simple table. We've got 3 satellites, and for each one we have an x, a y, and a z coordinate. It's clean, you know? It's organized. You've probably used a spreadsheet that looks exactly like this 1,000 times in your life. Well, all a matrix does is take that exact data, the numbers 7,000, 0, 0, and so on, and strips away the borders and text to hold those exact positions in one unified mathematical block. So, formally, here's your incredibly simple definition. A matrix is just a rectangular arrangement of numbers organized into rows and columns. That is literally it. It's just a compact, super-structured way to store the massive amounts of data we were just talking about. Instead of dealing with 9 separate, messy, disconnected variables for our 3 satellites, we just wrap them up into a single, neat package. It really is the ultimate organizational tool for complex engineering info. Section 2. The Matrix Machine. Dynamic Transformations. Now, what's really interesting here is think of the famous equation A times x equals b, not as some abstract algebra, but as a literal assembly line. Step 1 is your raw material, your input vector, which we call x. Step 2 is your factory floor. That's the transformation by matrix A. The matrix actively processes, stretches, or moves that input. And then step 3 gives you the finished product, your output vector B. Whether you're building aircraft control systems or programming robot motion, this 3-step matrix machine is what actually makes the system do something. And to make that machine actually work, we use matrix multiplication. Now, sure, unlike ordinary numbers, matrix multiplication follows special rules, multiplying rows by columns to find where data intersects. But don't get bogged down in the arithmetic mechanics right now. The real power here is how multiplication takes multiple variables and weaves them together. It lets engineers instantly calculate how a change in one single input perfectly cascades through an entire interconnected system to build complex relationships.
Section 3. The Mathematical Steering Wheel. Rotation Matrices.
Imagine a spacecraft rotating in a vacuum. On one hand, you have the object itself. That remains physically unchanged, right? The satellite didn't magically turn into a different piece of metal just because it turned. But mathematically, well, because the spacecraft moved, say, transitioning its orientation relative to an Earth-centered inertial frame, essentially a global view, to a local northeast-down frame, which is a localized view, its coordinates absolutely must change. The rotation matrix seamlessly bridges that exact gap.
In practice, a rotation matrix acts literally like a mathematical steering wheel for engineers. It allows mission planners to virtually rotate a satellite, totally swap out coordinate systems, describe really complex aircraft attitudes, and seamlessly transform vectors between entirely different reference frames. Without matrices acting as this crucial steering wheel, correcting the pitch of a commercial airplane or, say, navigating a rover on Mars would be mathematically impossible.
Section 4. Powering Modern Engineering. Space Applications. Prepare to be amazed because matrices are the invisible engines behind practically everything we rely on today.
Orbit determination, spacecraft state vectors are calculated and propagated using matrices. Attitude control, that spacecraft orientation relies completely on those rotation matrices we just talked about. The GPS and GNSS on your phone. Every single position estimation is a heavy matrix calculation. Those incredibly complex Kalman filters, the algorithms making accurate predictions through messy, noisy data in autonomous cars, almost entirely matrix operations. And artificial intelligence? The complex neural networks driving today's AI revolution are, at their core, just layers upon layers of matrix algebra performed at an absolutely enormous scale.
Section 5. The language of relationships. The true language.
By mastering matrices, you aren't just learning how to organize data into a neat little grid. You're actually unlocking the foundational language required to explore the absolute most advanced engineering concepts in existence. Understanding matrices means you are now fully equipped to dive into eigenvalues and eigenvectors, state space models, orbit dynamics, and the bleeding edge of machine learning. It really is your key to unlocking the next level of technology.
So, the crucial point here is perfectly summarized by this idea. Vectors describe quantities. Matrices describe relationships. Think about the profound difference there. A single number or a vector can really only ever tell you how much or where. But a matrix tells you how all those different moving parts interact, relate, and actually affect one another inside a complex system. And since modern engineering is fundamentally about understanding how different parts of a system interact to achieve the impossible, my final question to you is, are you ready to stop just counting isolated numbers and start mastering the hidden relationships that actually run our world?